Yes, welcome to the class on today's class on comparison of some of the parameters of CMOS and bipolar. Okay, and here we'll be listing out some of the parameters of the CMOS and bipolar. What is the difference? Just like what we discussed, the difference between the CMOS and bipolar technology, like input impedance, scalable threshold voltage, and your drain and source interchangeable in CMOS, whereas collector and emitter are not interchangeable, and input impedance is high in CMOS and input impedance is low in bipolar. Okay, and say your package density is high in CMOS and package density is low in bipolar, like this. Those parameters we have discussed, but here we'll be discussing some of the other parameters of the CMOS and bipolar and comparing that. Okay, first we'll take up the drain current. Okay, the first one is the drain current. Now drain current in case of CMOS is given by IDS equal to mu C naught W by L by 2, that is mu C naught by 2 into W by L into bracket VGS minus VT whole square. It is in saturation, or say this can be written in this way, or we know that in terms of beta we can write this as in terms of beta as beta by 2 into bracket VGS minus VT whole square. Okay, where your beta, you know that beta is equal to what? Beta is equal to KW by L, you know that. Okay, so we can write like this. The same way we can write here IDS, the drain to source current, is now analogous to in bipolar what? IC, and that IC is equal to what? Your IS, that is the maximum saturation current, into exponential E raised to Q VBE divided by small k into T. So what is this? Here if you just observe, that is E raised to, so if you just observe this here, IC equal to IS into E raised to Q VBE divided by K into T. What is this K? Boltzmann constant. What is this T? It is absolute temperature in Kelvin. So it is a constant and maybe at room temperature. Okay, and your IC is exponentially related with your VBE in this case. So that's why you observe that when IB varies, your IC varies little exponentially. Okay, so this is expression for IC in case of your BJT. Okay, whereas it is in case of your CMOS, your IDS is given by this equation. Now you can see IDS depends on voltage. Here your IC depends on here your VBE, where IB depends on VBE. In turn I can say IC depends on IB. So current control device, voltage control device. Okay, and next parameter, say second one. So second one is GM. So GM in case of your MOSFET, I can say that it is given by under root of 2 beta into IDS, or can also be written as like this: 2 beta raised to half into IDS raised to half. Both are one and the same. Whereas the GM in this case is given by IC divided by KT by Q, and this whole thing comes in the denominator. How I get this? Just I'll take a small derivation. So for which we know that your GM is given by, for MOSFET I'm saying, GM is given by what? Beta into bracket VGS minus VT. Already we have derived this equation, correct? And similarly your IDS is equal to what? IDS is equal to your beta by 2 into VGS minus VT whole square. That is in saturation in case of MOSFET. Now taking these two equations, I can simply rewrite. How? What is VGS minus VT from this equation? From this equation I can just write your VGS minus VT, taking square root on both sides. What I get is equal to 2 IDS and divided by beta, correct? This is whole square, but this is under root. Is it right? So simply taking square root on both sides, at LHS and RHS and interchanging, I get like this. Is it right? See, VGS minus VT whole square is 2 IDS by beta, 2 IDS by beta square root. So it is VGS minus VT, it is under root of 2 IDS by beta. Okay, that is what I can write. So now you can just see, I can simplify this. Now from this you just observe what is GM into GM is equal to beta into VGS minus VT. I can substitute here. See what is GM is equal to? GM is equal to beta as it is VGS minus VT. What is VGS minus VT from this? It is nothing but under root of 2 IDS divided by under root beta. I will separate out. See, under root of 2 IDS by beta is nothing but root 2 IDS by root beta, correct? Now, beta by root beta is equal to what? Root beta I can write it as what? Root beta into root beta. So, it will cancel. So, I can now write this implies your GM is equal to root of beta into root of 2 IDS, correct? So, you can just see this equation and this equation are the same, correct? 1 minute. Now I can say that here the GM is equal to root beta into into under root 2 IDS, which means that this is nothing but, you can see, if I call this as equation B, this as equation A. What is equation A? It is under root of 2 beta into IDS, or 2 beta under root and IDS under root of IDS. See, equation A and equation B both are same, correct? So I can say equation A and B both are same. That's how I get this. I have just derived it. Okay. Similarly, I can derive for GM. GM is equal to what? IC divided by in the denominator KT by Q. Call this as some equation X. Now just see how I write this. GM is equal to what? GM is equal to given by this. So now what I do is I take now your this IC divided by KT by Q. How I write? Just see how I derive that equation. I start this equation. I start with this equation. IC equal to IS into e raised to Q VBE by KT. Okay. Now differentiate this equation with respect to VBE. How I write? Del IC by del VBE is equal to IS, since you know that IS, Q, K into T, they are constant. Okay. So it is something like some constant into e raised to some K into X. So e raised to K into X is what? Differentiation. It is e raised to K into X into differential of the exponent. What is that? K. So what I get? Constant, a constant into e raised to X means Kx means e raised to Kx as it is into differential of this. What is differential of this? Q by KT is constant. Q by KT is constant into differential of VBE with respect to VBE. What I get? 1. So I get Q by KT into 1. Okay. Now simplify this. How I write? IS into e raised to Q VBE by KT into this Q I transfer to the denominator of denominator. What I get? KT by Q. But what is this? IS into e raised to Q VBE by KT is nothing but, from this equation, is nothing but what? IC. So I write this as IC. So this as IC. IC divided by KT by Q, correct? And call this as equation C. And now you can see, compare equation C with X. C is given by what? GM equal to your IC divided by KT by Q, both in the denominator here. Similarly, X, you see, this is also GM equal to IC divided by KT by Q in the denominator. That means you find that your equation C and X both are same. Okay. This is how I have written. Okay. Now, the next another parameter is your current density. Suppose current density is IDS, what I have written here in this case. Simply if I divide this by the cross-sectional area of the MOSFET. What is the cross-sectional area of the MOSFET? It is W into L. Okay. Channel length, channel width. W into L is a cross-sectional area. So if I divide LHS and RHS of this equation by A, what I get? See, IDS by A into mu C0 by 2L square into VGS minus VT whole square whole divided by A, correct? So this equation, I divide LHS and RHS by A, means A equal to W into L. So I call this as equation 1. So divide this by A on either side. What I get? IDS by A. Next, mu C naught by 2L square, mu C naught by 2L square. Okay, so this is nothing but now here, mu C naught by 2L, mu C naught by 2L, yes, correct. See here, mu C naught by 2L, sorry, it's not L square, mu C naught by 2L into VGS minus VT whole square as it is, into VGS minus VT whole square divided by 2L, okay, W by L, same thing, equation as it is I have written, W by L, okay. Next, see here, divide by A, on either side divide by A, here also A, what is A? A equal to W into L, substitute that, what do you get? W will cancel, so denominator what I get, numerator I'll get mu C naught into VGS minus VT whole square, divided by 2L into L, 2L square, so I get like this. Now it's nothing but what IDS by A is nothing but mu C naught by 2L square into VGS minus VT whole square, correct? And this is what I can now write for the current density for CMOS. Okay, what is current density for your bipolar current density? How I get? See, to derive the expression for current density for your bipolar transistor, what I get? Just see how I do it. I start with this, already I proved this, IC divided by KT by Q. See, in this case, but this is little complicated, so I directly write IC by A is equal to 1 by RB mu into tau B. But already we have written the expression for this IC. So here also you can divide by A on either side and prove that this IC by A current density in case of your BJT bipolar, okay, and prove that is equal to some value RB into mu into tau B, where your RB is called base resistance and tau B is called the transit time. Tau B is called the transit time, and your mu, so it is nothing but your mobility. Okay, mu is your mobility. So anyhow, since it's electrons, so we consider this to be constant. Now you find that here tau B is the transit time is very small. So when it is very small, this quantity becomes very high, which means the left hand side is nothing but a current density IC by A is very high. Okay, so current density in case of your bipolar is very high compared with your CMOS. Now I can say for CMOS, current density in CMOS is much smaller than current density in BJT, or in fact it is around 5 times less. Means current density in CMOS is 5 times less than current density in BJT. That is what I can conclude. Hope it is clear, students. So you can just understand this, right? Okay, students, now we'll consider the latchup in case of CMOS. So first, what is latchup and why latchup occurs? Okay, first we'll discuss about what is latchup in CMOS. Latchup in CMOS is nothing but now it's a condition. It is a condition in which the parasitic components, they give rise to the establishment of the low resistance conducting paths between the VDD and the ground, or else it creates a latchup is now a condition, a state in which the parasitic components which are present in the CMOS devices or a CMOS circuits, it gives rise to an establishment of very low resistance path, the conducting path between the power rails, that is VDD and ground, and that is called latchup. Okay. Now this latchup in case of your CMOS, how it occurs? See, the latchup in case of a CMOS is caused mainly by the glitches on the supply rails. See, these are the supply rails, VDD and VSS, these are the supply rails. Okay, VDD and VSS, these are the supply rails. So now if the glitches occur in these supply rails, or if the radiations occur on these supply rails, then latchup is caused. Now just to repeat, what I mean by glitches? The glitches is nothing but now a very small current flow, right, or a small voltage that is being induced here due to say sudden change in the voltages near in the vicinity of where the device is operating. Suddenly suppose there is a voltage appearing there, That means now due to the inadvertent appearance of the signals that are passing through the transistors, in that case there may be some voltage rise here, there may be some voltage rise here, so that causes a glitch. And a glitch is something like a voltage spike that appears. Glitch is nothing but a little voltage spike that appears on the power rails. Okay, or due to the incident radiations. That means if the CMOS device is operating nearby a machine, say suppose if a DC machine or a water pump or any electrical machines are operating, and suppose if you are operating the CMOS IC nearby that time radiations will enter here. Okay, so in that case I can say due to the incident radiation. So due to the incident radiations or the glitches on the supply rails, a latch-up will occur. Okay, that means a voltage is induced there, as a result the current will flow and the latch-up occurs. We'll see how it happens. Okay, so first I said what is latch-up. Now why it occurs I said. Now we'll consider how it occurs. Why it occurs is due to the glitches and supply rails. Okay, that is what here is indicated here. Clear? That is what is indicated. The parasitic components which are being shown here. Just see, it is no P-well structure. See, this is a P-well. Already we have studied about the P-well construction of CMOS, N-well construction of CMOS. Okay, previous chapter. Just recall that. Just see, this is a P-well. In P-well we know that NMOS is fabricated. So this is N and this is N. And this is your substrate contact. And this is your N substrate, which means PMOS is fabricated, and this is your substrate contact is this, this is substrate contact, this is a well contact. So this is your N, which means this is your NMOS. So this is NMOS and this is PMOS. Okay, in P-well we have what? N substrate means what? This is your N type. So N channel is formed, which means here in this this is, now you can see VDD is connected here. So you can now see in case of a P-well, which type of transistor is formed? P-well. Yes, P-well, it is NMOS is formed. In case of a N substrate, a PMOS is formed. So this is your PMOS and this is your NMOS. Okay, you can just consider this way. So that means now you can understand this is your, you can see this is PMOS. Correct? That's why it is shown PNP transistor. That means this is a parasitic element. That means due to the very fabrication of your CMOS using P-well structure, you find there is a parasitic transistor that is formed. That means this is your P, that is your substrate, that is a source. This is a drain. P type, P type. This is N type. Okay, and this is a base. P, N, P. What is this P? Is nothing but P-well. So this forms your P type, this forms your P type, this forms your N type. This gives rise to a PNP transistor. Okay. Similarly, come to this now. And what is this? P type. And what is this? N. And what is this? N. So N, P, N. Due to the very construction of this P-well structure, I get now NPN transistor being formed here. Next, this P-well has got some resistance. So that is appearing between your substrate contact and the well. So that is called RP. It is well resistance. Similarly, there is substrate resistance. So your substrate resistance is something like this. You can just see your substrate resistance. You can see this is RS, correct? Substrate resistance RS comes between this point. See, what is this? I said P, and between P type of this and your base. What is this? This is P type and this is N type. So which means this is your substrate resistance appearing here. Okay, so I get some resistance being connected here. See, remember this circuitry is shown here. Not that we are fabricating in this way. We are fabricating actually your P-well and N substrate, all these construction we have seen. But due to the fabrication itself, this particular circuit is automatically formed. That is what we call it as a parasitic elements. So when a parasitic components which are now appearing as like this, now equivalent circuit, the same circuit, I can just show it like this here. See, correct? So I can just show it like this. So you can just observe this here. It is P RS substrate. See, between VDD and the base of your PNP, RS is coming, correct? See, between VDD and the base, RS is coming. Between VDD and the base, RS is coming, correct? And between VSS, here, your RP is coming between what? VSS and P-well, correct? You can see here. Between base and your VSS, RP is coming, correct? Same thing. Now this is NPN transistor, this is PNP transistor. Okay, you can now see this here, right? So you can just observe this here. Now you can just observe this here. So that is it is nothing but equivalent circuit for an SCR. SCR probably you have studied in power electronics. Okay. Now suppose due to the incident radiations or the glitches, some current is induced. When some current is induced, there is a voltage drop here. So when there is a voltage drop, what is the drop across this? Some voltage V, and that is connected. RS is connected between what? Between base and emitter of T1 VBE. Suppose if this VBE is more than the cut-in voltage of this PNP transistor, what happens? By transistor action, it starts conducting. When it starts conducting, what happens? Current begins to flow from emitter to the collector like this. So there is a collector current flow here. When there is a collector current flow here, part of base current also flows here, some current also flows here. When some current flows here, then the voltage drop appears across RP. Then what happens? What is this? It's nothing but VBE of what? Of transistor T2, which is NPN. And suppose if this voltage is more than VBE of T2, then this will also conduct. So this is also conducting, this is also conducting. Now see, collector current feeds the base current. That means collector current begins to flow directly. Now collector current flows here. Initially this is on and the drop appears here. This turns on and the current is drawn. Initially this is cut off. First this turns on and there is a current flow, and VBE more than V gamma, this T2 turns on. When T2 turns on, collector current begins to flow through T2, and as a result the base current will flow here, and collector current will flow through this. So this will increase, and further this will increase, this will further increase, and this will further increase. That means as a result there will be a lot of current flow between VDD and ground. See, on, which means this VC is at, VB is at. Simply VC is at, VB is at. We know that VC is at and VB is at, they are very low potentials. That means between VDD and VSS, a very low conducting path is created. That means RS and RP will never come into the picture at all. That means as a result, a lot of current will flow from VDD to VSS. What happens? Then it may result in the spoiling of the transistor. That means current gets latched. That is called latchup in CMOS. Because of the latchup, what happens? Transistor action fails. CMOS will never work as CMOS now. Okay, this is a disastrous result. That is what we say. Low conducting paths are created due to the parasitics between the power rails VDD and VSS. Okay, I think you understood by this. This I explained using your P-well structure. The same thing holds good here. See, ACR characteristics already you studied. Your voltage V versus current I. See, initially when I increase the voltage, when this voltage increases at a certain level, suddenly transistor conducts and the enormous current will flow. That means latchup occurs. Suddenly the current shoots up. Okay, and if at all I want to reduce this current, I should reduce this voltage so that current falls below the latchup current. In that case, only it turns off. But you see here, there is no other question. That means the transistor may be spoiled. Okay, so this is a drawback associated with latchup. That means here, once latched up, this condition will be maintained until the latchup current drops below IL. I said latching current. Once it falls below, then only it turns off. But that never happens here. So that means you find that your VL and IL are not readily achieved in the normal mode of operation. Okay, that means we should ensure that CMOS process, we should operate in such a voltage that the voltage should never exceed this VL, and latchup current through that we should not exceed the latchup current. But that is not possible because incident radiations and your glitches sometimes we cannot avoid. So latchup will occur. Okay. Similarly, just see latchup in case of your P-well structure. See P-well, this is N-well structure. In N-well, same thing. In case of P-well, we have seen N-type transistor. In N-well, PNP transistor. And in N substrate, we have seen PNP. But in P substrate, we use, that is a NPN transistor is formed. See, this is also exactly the same. Only thing is, in this model, what is shown, your PNP is nothing but NPN here, and here this is NPN. Instead of NPN, it becomes PNP. That's all. Rest all is same, and VDD and VSS are interchanged. And here also same thing occurs. Okay, in case of your N-well structure. Okay, so your N-well and P-well, say you can. It is shown here due to the parasitics. So if you are asked to explain for N-well using this model, you should explain. If you are asked to explain using P-well using this model, you should explain. Okay, but I clearly explained using the model for P-well. Same explanation holds good, except your role of NPN and PNP will change, and your RP, P well resistance. Here also P well resistance. See RP. Here also your N well resistance. See instead of P well, here is N well resistance Rn, and instead of Rs remains same. Substrate resistance here also. Okay, and you see substrate here is NPN but PNP previously, and here is PNP but there it is NPN. Okay, that is a change, and VDD and VSS now it is interchanged. Okay, see in the P well N well structure VDD comes, but here you see, here if you just see your N well structure, in the P well structure VSS comes, so that is the only change. So VDD and VSS are interchanged in case of the wells. Okay, so that is what you find the difference. But what is the solution for latchup? Solution for the latchups are now some 2-3 remedies are mentioned here. So one is, you can see, that is substrate doping levels, means here this doping concentration here, if I reduce the substrate doping concentration, what happens? There is a drop in the value of Rs. See, that is substrate doping levels. If we increase, usually doping concentration increase means what? It is more and more carriers, means what? Less resistance. That means less Rs. Similarly, here also doping concentration, if I increase the well, obviously your Rn will reduce. When I reduce Rn and Rs, then I can avoid latchup problem, right? And sometimes we use the guard rings. Using guard rings also we can reduce the latchup. Okay, that is beyond the scope of the syllabus, so I'll be not explaining much about the guard rings, but you just remember, by the introduction of the guard rings also you can avoid latchup to some extent. But how reduction in Rs and RP will reduce the latchup? You can see here. See, if Rs or RP is reduced, what happens? See, why this T1 is conducting? Because the current flow in Rs, so there is a voltage drop. But suppose if Rs is less, what? When the glitch occurs, current flows, but some very small current flows. But Rs is also less, means what? Voltage drop is also less, means VB is also less. If VBE, even if the current flows here, means glitches will occur or radiations will occur, that we can't avoid, say, in that case. But due to the current flow here through Rs or through RP, it is the current is less, but resistance is also less. So voltage produced or voltage developed across RP or Rs is very small. Small means how much? Less than V gamma of T1 and V gamma of T2. What happens? T1 will never conduct or T2 will never conduct. As a result, latchup will not occur. I repeat, by reducing Rs and RP, though the glitch current flows through this due to the glitches and radiations, but the voltage developed across Rs or voltage developed across RP is much smaller than cut-in voltage of the transistors. Hence, transistor will not conduct, latchup will not occur, or latchup is avoided. That is how, this is one of the solutions what is being shown here. Okay, by controlling RP out in the fabrication parameters. Okay, and low contact resistance, etc. So like this we can reduce. But in case of BiCMOS, see, in case of a BiCMOS, again here also the resistance, N-well resistance and substrate resistance we reduce. But there is one more, substrate resistance we reduce and N-well resistance we reduce. But we have one more, lateral current to invert latchup and higher value. See, in that case you have one thing, that is parasitic elements which are being introduced there. So we have there the one is called the buried subcollector. Buried subcollector, the resistance is very small, and because of that reduction, Rs and Rw means a larger lateral current is necessary to invite, means the latchup to occur. The same thing as the previous. So higher holding current, which means latchup is avoided by reducing Rs and Rw in case of BiCMOS. How we reduce? By using buried subcollector. Okay, and one more thing is your beta value is also reduced in case of your the BiCMOS circuit. The beta is now ratio of IC to IV, that is reduced. How? The gain, we just try to reduce it by the construction process of BiCMOS itself. So as a result, the PNP transistor in case of N-well latchup circuit has a beta reduced owing to the presence of the buried N plus subcollector. You see that same thing I explained. And this has the effect of reducing the carrier lifetime in the N base region, and this contributes to reduction in the beta. That means how beta is reduced? Beta is reduced because of the carrier lifetime in the base region. What is the meaning of carrier lifetime? Means the carriers, the charge carriers, though they are produced, but they exist for a short duration of time. Momentarily, thereafter they will simply recombine. So as a result, the beta is reduced, means it will not contribute to the gain. Current gain is reduced. Beta is reduced, means current gain is reduced. Hence, you see how that will bring avoid the latch up. You see here, when the small current flows here, there is also current flows here, but because beta is less, due to small increase in IB, there is a small increase in IC. But if beta is large, there is a small increase in IB, there is a large increase in IC. Suppose if beta is less, what? Small value of IB brings small change in IC. So it means that suppose if that current is very much smaller for the transistor T1 to conduct, then obviously it will not enter into latch. So that means beta is reduced, as well as see, sometimes we try to control these parameters using some 2-3 values. So in all angles we try to attack. Okay, so that is how I can say it here. Is it clear? So I think I elaborately have explained for BiCMOS, say how the latch-up is avoided, and for practical aspects you can see the BiCMOS latch-up occurring is much less compared with your CMOS in P-well or N-well structure. But in twin tub, you see it is still less. Okay, twin tub is still less. But there also we have to reduce RS and reduce your RP there also. Okay. So I think with this we'll be concluding our discussion on your latch-up in CMOS. Students, you watch these videos, and just if there are any questions, you come back with the discussions of the questions. Hope it's clear. Thank you. Okay.